In our final video on work and energy, we are going to put all of the pieces together by discussing one of the most core concepts in all of physics, and arguably one of the foundational tenets of all science, the law of conservation of energy. Now, I know for a fact that many of you are already very closely acquainted with this law, and in fact, I would not be surprised if almost all of you could give me a nice, quick, brief description of what this law is, because what you probably learned it as is, well, that energy can neither be created nor destroyed. It doesn't just pop into existence. It doesn't just disappear. It must go from one place to another or change from one form to another. And this is exactly correct. However, we are going to relearn how to think about it just a little bit to make it more applicable to the types of problems we're going to see and the types of scenarios we're going to see. So how we're going to use it in this class is we are going to define it as in a closed system, the mechanical energy is constant. Okay, now a couple key words here. First off, we know what closed means now. We've looked at this a few times before, and remember this means no net external force on the system. If we say the mechanical energy is constant, we're ultimately saying it's conserved. It's a conserved quantity. It's not going to disappear. And mechanical energy, and we're going to get more into this in a second, remember we're talking about very specific types of energy. So ultimately, just as we already kind of knew, this is no different. That within a closed system, though, energy, specifically mechanical energy, can be moved from one object to another or transformed from one type to another, or maybe some combination of the two. Mathematically, this law can be stated pretty simply, that the mechanical energy of the system initially will be equal to the final mechanical energy of the system. Well, what exact types of energy go into mechanical energy? Well, we're going to have kinetic, gravitational potential energy, and elastic potential energy. So that tells us that if we have the initial kinetic, the initial gravitational potential, and the initial elastic potential all combined together, well, that those have to equal their sum at the end as well. And frankly, they need to be equal to each other at every single point in a particular scenario. So we can actually look at multiple points in time, that energy should still be the same. Now, I really want to mention that mathematically, this is not very complicated. And in fact, most of the calculations we'll be doing with energy are pretty simple. We know the kinetic energy is 1/2 mv squared. We know the gravitational potential energy is mgy, and we know that elastic potential energy is 1/2 kx squared. And we're just doing really some addition and some simple algebra. The math's not very hard. Instead, the difficulty here is not solving the problems, but really setting them up and knowing how to look at a particular situation and apply the law of conservation of energy properly so that we can then undergo fairly simple mathematical processes. So what are some tips that we can have to make sure we're setting this up properly? Well, one, we need to focus on the types of mechanical energy present at each moment in time. If we look at one instance in a scenario and another instance, is there kinetic energy, gravitational potential energy, elastic potential energy, etc. Two, remember if we are using potential energy, we need to make sure we define our system correctly. So if we're using gravitational potential energy, you need to include Earth in the system. If not, it won't be closed. And if you have elastic potential energy, you need to include the spring in the system. And lastly, if there is an external force, so it's no longer a closed system, mechanical energy is often lost as thermal energy. So looking at this law, sometimes you'll see it written this way, and it's not a bad way to think about it, that we could really add a thermal energy term to the end, that you're going to have some initial mechanical energy, at the end you're going to have mechanical energy, plus whatever was lost as thermal energy. Now, a lot of times we can ignore that. That's really only going to be useful in certain situations, in particular if we're looking for that, or if we're trying to see if energy is in fact conserved. Now, before we start analyzing some more complex scenarios, let's talk about a useful tool that we can employ known as energy bar charts. So energy bar charts are kind of what they sound like. They are bar charts that show us the different types of energy at some moment in time, and they help us define, okay, what types of energy are there, and additionally, how are those types of energy related to each other proportionally? How much of one do we have versus another? So let's look at a scenario here. Let's say we have a spring-loaded, like a dart gun. For instance, we're going to have that spring-loaded launcher. We're going to initially push the dart in. It's going to be loaded. We will pull the trigger, and this dart will fly through the air in a nice parabolic arc and hit the ground over here. So let's look at this situation through multiple points, see how we can use energy bar charts to analyze what types of energy, mechanical energy specifically, are present at every moment in time. So at the very, very beginning, let's say we have the dart loaded into the launcher, and I didn't draw that here, but imagine it's loaded in, the spring has been compressed, and the question is, well, what types of mechanical energy are in the system at that moment in time? Okay, well, we need to go ahead and define what our system is. So let's go ahead and do that first. Well, we have a spring. We're going to probably have gravitational potential energy because it's going up. So we need to make sure we include the dart, the earth, and the spring in our system. I'm going to go ahead, as I did here, and define y equals 0 at this point on the ground. And we're going to go ahead and say we are launching it from ground level, just to keep things a little more simplistic. So what type of energy do we have initially? Well, the dart's not moving. There's no gravitational potential energy because we say it's at ground level. So initially, the only type of energy present is elastic potential energy. And all of the mechanical energy of the system will be elastic potential. But then what happens when we fire the dart? Well, when we fire the dart, first off, is energy going to be conserved? Well, we include the spring in the system and the dart, so they're the only two things applying forces to each other, so that's within the system. Mechanical energy must in fact be conserved. So, as it gets launched from the launcher, what exactly is it going to have now? Well, it's moving, so we're going to have kinetic energy. It's moved a little bit above ground level, so we're going to have at least some gravitational potential energy, but the spring has now been uncompressed, so we're not going to have any elastic potential. So I'm going to go ahead and give an estimate. I'm going to say that it's mostly going to be kinetic with maybe some gravitational. And let's look forward a little bit more in time. When this dart has risen a bit more in its arc, well, what do we have now? Still no elastic potential, so I don't need to worry about that. In fact, I'm going to go ahead and start crossing out the ones I don't have just to keep myself a little more simple. So we're not going to have that. Well, what happens as it goes up? Well, as it's going up, it's getting further and further away from Earth, so the gravitational potential energy must be going up. What about the kinetic energy? Well, we know it slows down as it goes up, so we should imagine that the kinetic energy will go down. But let's say you weren't sure. Well, let's look at these scenarios so far and notice that at every point, these bars need to add up to some total mechanical energy E, because the total mechanical energy is conserved. So initially, it's all elastic potential. When it becomes, at this moment in time, kinetic and gravitational potential, if I stack this bar on top of this one, they should add up to the same mechanical energy E because it has been conserved. Okay, well, if I go to the next point, well, if I'm going to have some more gravitational potential energy now, I have to combine it with kinetic to get the same total mechanical energy. So if gravitational potential energy is going up, kinetic energy is going down. And in fact, let me go ahead and draw that right here. And another way to think about it is the kinetic energy is being transformed into gravitational potential energy as the dart continues to rise. Now, this is in fact going to keep happening until we get to the top of the arc. As it goes higher, we get more gravitational potential energy because more kinetic becomes gravitational potential. And at the top, even more kinetic becomes gravitational potential. Now note, if this was fired straight up and down, it would be at rest for an instant at the top, and we would not have kinetic. However, this is a projectile at an angle, so it's still moving at the top. So we're going to just have a little bit of kinetic, a lot of gravitational potential, but once again, if we add these bars together, we would still be adding up to the total mechanical energy E. All right, so let's look at a couple more points further down. Let's say if we look at the dart as it comes down, well, as it comes down, what determines the amount of gravitational potential energy is just the height. So whatever the gravitational potential energy was here at this height should be the same here at that height. And in fact, I'm going to get that. So these should look, this one and this one, and this one and this one should look very similar because they're at the same height. So the same amount of gravitational potential energy, same amount of kinetic energy. And we learned way back in projectile forces that this makes sense because it's a fairly symmetrical situation. So what's going to happen at the instant right before it hits the ground? So right before, it's like infinitesimally above the ground. Well, we can say the gravitational potential energy should basically be 0 at that point. It's going to be so tiny, we can consider it to be 0. There's still no elastic potential energy, so all of the mechanical energy should be kinetic at that point. And then lastly, well, what happens when it hits the ground? Well, when it hits the ground and gets, let's say it gets stuck, it sticks into the ground. Well, it's not moving, so there's no kinetic. There's no spring, so there's no elastic potential. It's at ground level, so there's no gravitational potential. So, well, that means there's no mechanical energy at all. And how is that possible? Well, that's because the ground is acting as an external force on the dart. Now, that may be a little weird to think about because we said our system included the dart, the earth, and the spring. Why would the ground not be part of the system that the earth is? But remember, we're talking about like some surface here. Imagine instead of hitting into the ground, it was fired on like the second story of a building or something, and it hits somewhere on the floor on that second story. Well, then it would be the floor applies the force, not the earth. So we can separate those two away from each other. And where did all that mechanical energy go? Well, honestly, it went to thermal energy with the ground, maybe a little bit of sound energy and things like that. So it's still there, but the mechanical energy is not conserved because of this external force on our system, because our system did not include the ground itself, just the dart, the earth, and the spring. So looking at this, what is the key idea we can get using energy bar charts? Well, it allows us to know that if we stack them all up, they should always equal this total mechanical energy E, and that helps us think about, okay, well, how much energy has been transformed from one type to another? How much do we have at some particular moment in time? And now using the equations we have for the different types of mechanical energy, we can start to reason out some more details. Well, now that we've discussed how to look at these types of situations, let's start reasoning through one to see how we can apply the law of conservation of energy to a particular scenario. So let's say we've got this scenario here. You probably want to go ahead and draw this in your notes. Let's say we have a block starting from rest at the top of an incline, and it's going to slide down a frictionless slope, so we don't have to worry about friction. After reaching the bottom, it continues sliding on a horizontal frictionless surface until it reaches a spring, and it's going to compress the spring, which will bring the block to a stop. Now, granted, we could also say after that point the spring would come back and push the block backwards, but we're going to go ahead and stop looking at the situation at that moment when the block comes to rest. And we want to determine a few different quantitative factors. One, what is the block's speed when it is halfway down the slope? Two, what is the block's speed as it slides along this horizontal surface? And three, what is the distance that the spring will compress when the block comes to a full stop? Once again, as I said earlier, the mathematics here aren't going to be that hard. What's really going to take most of our time is analyzing every moment in the scenario and figuring out how to really set up the problem. So let's go ahead and do some things that we should automatically do at the very beginning of any exercise like this. And the first one is define our system. What is going to be in our system? Well, the block, for sure. We see that we're going to have some gravitational potential energy because it's at a height, so we definitely need to include the Earth. And we have this spring here, so we need to definitely include that as well. Well, what about our slope? Do we need to include that? Probably not, because one, it's frictionless. We don't need to worry about any force of friction. And although it is applying a force to the block, keeping it from going straight down, the source of the net force is actually going to be the gravity pulling it down the slope. And we've already included the Earth in the system. So that's probably enough, the block, the Earth, and the spring. And let's go ahead and additionally, to make my life easier, I'm going to define my bottommost point as y equals 0. Well, now that we've defined the system, let's actually go ahead and draw energy bar charts for the specific relative moments in time that we are looking at here. And that's going to help us figure out, okay, what types of energy do we have present at each moment and kind of in what proportion should we be considering? Well, at the very, very top of the slope here, we are going to have what? Well, initially, our initial mechanical energy, it's not moving. There's no spring there yet. So all the energy is initially going to be gravitational potential energy. As the block starts to slide down the slope, it gains kinetic energy, and that energy comes away from the gravitational potential energy. It's being transformed, and the force there is the force of gravity, but the Earth is within our system, so that's okay. Mechanical energy is conserved. As it gets to this bottom point, once again, we've had some gravitational energy become kinetic energy, and it's going to continue moving on with no change in energy until it hits this spring. And when the spring becomes compressed, the kinetic energy will be transformed into elastic potential energy that will be stored inside the spring due to that spring force. But once again, the spring and the block are both in the system, so mechanical energy is still conserved. So we should be getting something. So we've got these 1, 2, 3, 4 moments in time, and we should be getting something like this. Now, a couple things we want to notice here. One, mechanical energy is always conserved because this is a frictionless slope. So we don't need to worry about losing any energy to thermal energy. If that was not the case, we would have to consider that. Secondly, these are pretty easy. This is all gravitational potential, all kinetic, all elastic potential. But how do we know the exact proportion on this one here when it is halfway down the slope? And there we need to be a little bit more careful. We know it has both gravitational potential and kinetic, but if it's halfway down the slope, that means it has half the height, especially because we defined our bottom as y equals 0. So it's going to have half of the gravitational potential energy. And where did all that energy go? Into kinetic energy. So this will be a specifically 50-50 split. If instead it was at 3/4 the height, it would be 3/4 gravitational and a quarter kinetic. If it was at 1/4 the height, it would be a quarter gravitational and 3/4 kinetic, etc. Well, now that we've set these up, what was the first thing we were asked to determine? The block speed halfway down the slope. So that means I care about this moment here and that moment there. I don't need to worry about these other two moments. I'm only caring about the initial setup and our setup when it is halfway down the slope. So let's go ahead and say, all right, well, the energy of our system is going to be conserved. So the initial total mechanical energy will equal the final total mechanical energy. And I'm going to go ahead and write out K naught plus UG naught plus US naught equals K plus UG plus US. I can automatically do that. But if we look at these two moments, initially, the only type of energy we have is gravitational potential. So that's the only one I need here. And halfway down, I have kinetic and gravitational potential, but I don't need elastic potential. And this means I can simplify things a bit. I can get rid of those terms, and I'm left with UG naught equals K plus UG. And now let's start plugging in some values we know. That we have mgy naught is equal to 1/2 mv squared, the equation for kinetic, plus mgy. So now that I'm solving for v, I can rearrange this, and I'm going to get mg, I'm going to move this across and get mg, this should actually be y naught minus y, but it's not going to change any of my math. Mg y naught minus y divided by the 1/2 m, and then I take the square root. And if you want to, you could even cancel out the masses here. I didn't for right now. We plug in our numbers, so we get 3.5 kilograms times 10 meters per second squared times half of the height, because that would be 4.2 minus where it's located now, which would be 2.1. So our change in y is 2.1 meters. Divided by 1/2 times 3.5 kilograms equals 6.48 meters per second. So that would be the velocity of the block halfway down the slope. Now, before I move on, I want to quickly note this is not the only way you could have done this. And some of you might have instinctively gone a different route. For instance, you could have maybe just solved for, okay, what is the total energy here, and then subtracted the energy halfway, and then solved. You could have done something like that. And there are many, many times when we can go about this in slightly different ways depending on what information we have. But this is the most fully written out procedure to go through. If you can skip steps because you are able to recognize some trends, that's fine. But this is the more careful way to approach it. Well, now let's talk about the second problem we had, which was what is the block speed as it slides on this horizontal surface? Well, we are going to once again have total mechanical energy conserved. I'm going to set this up, and I'm going to go ahead and once again go with my initial situation and my now final situation. So I'm not going to have any kinetic or elastic potential energy here. And at this point when it's sliding, I don't have UG or US, just K. So I can simplify that and say UG naught equals K, or mgy naught equals 1/2 mv squared. Once again, I can actually go ahead and cancel my m's out, and then multiply the two across, take the square root, and I plug in some numbers, and I get a speed of 9.17 meters per second at the bottom of the slope. Lastly, let's find the distance the spring compresses when the block comes to rest. Once again, I set up my law of conservation of energy, and I'm going to once again look at this initial situation and this final situation. You didn't have to do that. You easily could have compared it to this one or that one. Doesn't matter, but I'm going to do that now. So I'm going to say I only have gravitational potential at the beginning, and once the spring is compressed and it comes to a stop, the only type of energy I'm going to have is elastic potential. So I can start plugging in my equations of UG naught equals US. That should just be US, not US naught. So I get mgy naught equals 1/2 K delta x squared. And I'm specifically looking for delta x. So I'm going to multiply the two across, divide by K, and then take the square root and plug some numbers in, and we get that it's going to compress a total of 0.86 meters. Now, I could spend all day going through multiple examples of conservation of energy, but this is honestly something that's going to really come with practice, and we're going to do lots and lots and lots of practice in class until it practically comes second nature to you. So what are the main takeaways we have then right now for the law of conservation of energy? Well, one, can we determine if this law applies to a particular situation or not? Now, careful, it technically always applies. But when we're talking about is the mechanical energy conserved or not, then it only applies if the system is closed. If it's not closed, we are losing some of that mechanical energy to, for instance, thermal energy, sound energy, etc. Can we utilize energy bar charts to analyze what types of energy are present at different moments of time and in what proportions? Remembering that those always have to add up to the total mechanical energy. All the bars have to stack up to be equal to the total. And additionally, keeping in mind that when we have, energy bar charts that are changing as time goes on, it's because the energy is moving from one type of mechanical energy to another. It's being transformed in these processes. And lastly, can we analyze the system using the law of conservation of energy in order to determine various quantities from a given scenario like we did at the end? So, how to do that? Define the system. Consider drawing energy bar charts for all the relevant moments in time, and then compare multiple moments in time using the law of conservation of energy. Go with what you have, and then compare what you have to other moments. All right, this concludes our unit on work and energy. So, if you have any questions, let me know.